Good day, I'm Norman Wildberger. We are looking at the difficulties with establishing real numbers as infinite decimals. These are very serious difficulties which the professoriate these days is doing its best to avoid acknowledging. And there's good reasons for it, because the price to be paid, as we'll see, is quite significant. Or at least it appears to be. However, we'll see that there are great opportunities as well by acknowledging the difficulties and moving beyond them. Last time we talked about infinite decimals in terms of infinite choice sequences. The idea that it was possible to prescribe decimals one at a time, arbitrarily and independently, forever and ever. And we basically explained very clearly, I hope, the difficulties with that position. Today we're going to look at another approach to infinite decimals, the algorithmic or constructive or computational approach. In this approach, we think of an infinite decimal as being expressed by an algorithm. So the sequence of digits that we're trying to get at can be captured by an algorithm, or a procedure, or a function, or a computer program, or some equivalent method. So we really have these three positions. We have the infinite choice position, we have this algorithmic or constructive or computational position, and then we do have a third position, which is really the only one left to us once we acknowledge the difficulty or impossibility of the first two positions. And that third position is a finitist or rational position, which is that infinite decimals are illogical and unnecessary. And ultimately, this is the position that we are going to adopt. And I am going to try to show you that mathematics is not impoverished by this position, but actually unfolds before us in a brand new and exciting way. All right, today we're going to look at the algorithmic or constructive or computational approach to what is an infinite decimal. And we're going to look at the pros and the cons. Let me start by saying that I have a lot of sympathy for this approach to infinite decimals. I think this is a very reasonable thing to try to do. To try to look at an infinite decimal like 3.1415926 and so on, with digits that go on and on forever, by approaching that in the point of view that says, well, we need an algorithm that describes the digits. And we'll think of the infinite decimal as really being encoded by the algorithm. The beauty of that is that the algorithm is a finite object, and so we can work with the infinite decimal as represented by this finite object. I think that's a very sensible, reasonable, natural thing to try to do. The only problem with it is that it's too difficult to do, and ultimately we can't do it in the year 2012. Alright, so what do we mean, first of all, by an algorithm? Clearly, we need to think about what that word means. So, intuitively, we might say that it's a finite list of well-defined instructions that gives us a step-by-step procedure for a calculation. And often the calculation that we want to do is of a function. So this is an English language definition, something that you might find in a dictionary. I don't think at all that it's clear enough and precise enough for mathematical usage, but at least it gives us an initial orientation to what an algorithm is. Those of you who are familiar with computers can, if you like, think of it as being essentially a computer program. So what we have here, for example, is a piece of paper or a file on your hard drive with instructions. Instruction number 1, instruction number 2, perhaps down to instruction number 15. And these instructions allow us, for example, to calculate a function. To capture this number pi, the function naturally might input the place of the decimal and output the decimal value. So f of 1 equals 1, f of 2 equals 4, f of 3 equals 1, f of 0 equals 3, let's say, f of 7 equals 6, and so on. So the idea is you want to know what is the 1, 2, 3, 4, 5, the fifth decimal place. So you input the number 5, perform the operations on the number 5, eventually you get an output, and hopefully that output is the digit 9. And that's how we can specify the entire infinite decimal by a very finite, cut and dried procedure. It's a very attractive idea. An attractive idea which ultimately doesn't work. As we go down this route, it's clear that there are some significant challenges ahead of us. First of all, we are going to need an underlying theory or understanding of algorithms. We're going to have to know a lot about algorithms. What they are, how they work, how they're implemented. We need a theory of algorithms. Secondly, we're going to have to acknowledge that conceptually, this framework for establishing a number system is much, much more complicated than for rational numbers. Rational numbers, 1 6 plus 2 7 equals 19 over 42. What a rational number is pretty simple. It's a pair of integers. How we add them is reasonably simple. How we multiply them, reasonably simple. Here, what we're going to be dealing with is algorithms, computer programs. And we're going to have to deal with the challenge of how do you add them? How do you multiply them? How do you check the laws of arithmetic? It's a big challenge. We'll probably need help from computer science. Because we're talking about algorithms, the computer scientists know all about algorithms. They're the ones who work with these things. They have very elaborate experience and theories for them. However, within mathematics, there's also theory of computation. Mathematicians also study computation. So there's something called the lambda calculus. There are things called Turing machines. There's something called automata theory and other things as well. And the question is, will we need any of these theories in order to set up our approach to infinite decimals as algorithms? All right, so what are the pros and cons of trying to look at infinite decimals in terms of algorithms? Well, there are lots of advantages. There are lots of good reasons for trying to do this. The first one, perhaps, is that this general orientation agrees with the historical point of view. Historically, the infinite decimals that people dealt with were given by procedures, by algorithms, by rules that generated digits one at a time. For example, the square root algorithm, which we've talked about at several points in this series, going back to the Babylonians, the Hindus had such an algorithm, the Greeks, the Arabs, and then Newton for square root of 2, square root of 5, and so on. These are procedures that work step by step, and they allow us to get closer and closer rational approximations, which can be converted into further and further initial strings of a decimal. There's also a cubed root algorithm, which we haven't talked about, but it's some more sophisticated version of a square root algorithm. In fact, it was studied by ancient Indian mathematician Aryabhata around 500 AD. And of course, it's also accessible by Newton's method. And then we must mention pi, which plays a very big role in the history of people's fascination with infinite decimals. So pi has been tackled going back to Archimedes, who initiated a essentially algorithmic process for approximating pi. But the first, perhaps, modern formula goes back to an Indian mathematician, Madhava, from Kerala in southern India in the 1300s, who came up with this remarkable formula that pi is equal to root 12 times 1 minus 1 over 3 times 3 plus 1 over 5 times 3 squared minus 1 over 7 times 3 cubed, and so on. So each one of these terms is getting smaller because the denominators are getting bigger. Keep multiplying by the next odd number and then by powers of 3. So we're adding and subtracting smaller and smaller quantities, and if you go to a certain number of terms, then you can compute a relatively accurate approximation to pi, provided you also know how to take a square root of 2. And Madhava, in fact, was able to calculate pi to this number of decimal places using 21 terms of this series. Now, this is an algorithmic approach. You have a very cut and dried formula. You can go as far as you want in this formula. You can compute something. You get an initial part of the decimal. So in principle, you can keep going, getting more and more digits this way. So the decimal is encoded by this formula, which we could think of these days as also a procedure or a computer program, if we like. And historically, there have been many, many other formulas for pi. And in my next video, in fact, we are going to have a good look at pi and some of the many formulas that people have come up with that essentially give us algorithms for computing pi. All right, so historically, this point of view corresponds to what people used to think. Stevin, when he introduced real numbers in the 17th century, he would have been thinking about these infinite decimals in this algorithmic fashion, because the main examples that he would have had, like roots and pi, were of that form. And also, I suppose, repeating decimals, which are also a special and very simple example of an algorithm that generates digits. Another advantage to this algorithmic approach, if we can make it work, is that it allows evaluation of so-called infinite series. These are very important constructions in analysis, and the real numbers, as we currently have them, allow us, or seem to allow us, to evaluate these things. For example, consider this infinite series. So it's an infinite series in the sense that we're adding more and more terms, but the terms that we're adding are getting smaller and smaller, so we're converging to something, we think, and that something that we're converging to is a real number. Now this series here, the terms are actually forming a very nice and important pattern. Here we have 1 over 2, and then 1 over 2 times 3, and then 2 times 3 times 4, 2 times 3 times 4 times 5 in the denominators. So these numbers are called factorials. So we can write this summation more compactly using this summation sign introduced by Euler. So we're summing from n equals 0 to infinity 1 over n factorial. 1 over 0 factorial is 1 by definition, because 0 factorial is defined to be 1. There's 1 over 1 factorial, 1 over 2 factorial, 1 over 3 factorial, 1 over 4 factorial, and so on. So how do we approach such an infinite series? Through the idea of the partial sums, where we go from n equals 0 to some fixed natural number k. So in other words, we add up all the terms up to a certain amount and compute what we've got. So in this case, the first partial sum was just that first term, which is 1. The second partial sum, the first 2 terms, that's 2. Then the next one will be 5 halves as a decimal 2.5. And then when we add this term here, we get 8 thirds, which is 2.6 repeated. Then when we add this one on top of it, we get 65 over 24, which turns out to be 2.7083 repeated. And then S5 is 163 over 60. That's 2.716 repeated. S6 is this. S7 is this. And S8 is this, starting to get a little bit more complicated. Here the repetition only kicks in at this level here. Now if we look at all these partial sums, we see that they are sort of converging to something in the sense that the first terms start to stabilize after a while. So here we get 2.718, and here's another 2.718, 2.718. All the further terms are going to have 2.718 in them. So as we keep going, we end up generating more and more digits. So this is really an algorithm. It's really a step-by-step procedure that can be used to create an infinite decimal step by step, slowly, slowly, more and more. Here is the limiting value. The limiting value is a very important number called e. That's the base of the natural logarithms. It plays a very important role in mathematics. It's 2.718281825904523536027, and so on. And the so on now is represented by exactly this infinite series. And we can think of this infinite series in terms of an algorithm. It's laying out a procedure for calculating more and more of these infinite decimals. So the advantage is we don't need to think about the object itself as being this infinite decimal going on forever and ever and ever and ever. We don't have to become philosophical about what does forever and ever and ever mean, because we can just work with this formula. This formula is essentially encoding this decimal. The formula is a very finite thing. It presents us with a very simple algorithm that generates the decimal. So it's the same kind of idea as when we use something like this with the repeating decimal. We had some finite expression that actually encodes something that we can think of as going on forever, but the actual expression that we're using is finite. The expression is finite. It's a finite algorithm. So this is one big advantage, that infinite series can be summed this way. Of course, there's a little bit of a condition on this series. The series has to have the property that the terms that we're adding get small sufficiently fast so that there's some kind of convergence, so that we do actually end up stabilizing and that these things don't start wandering around as we add more terms. So not all infinite series are summable in this way, but the convergent ones are. And we do need this theory of real numbers, it seems, to sum them. And this is one big advantage in thinking about real numbers this way, in this algorithmic way, that it allows us to sum convergent infinite series. Another big advantage of the algorithmic approach is that it allows us to define many functions. For example, the exponential function, a key function in modern analysis, which we can define this way, along with Euler, the limit as n approaches infinity of 1 plus x over n to the n. So we're inputting x and we're outputting this thing. Well, this thing is really an algorithm, or it's a procedure that allows us to calculate more and more digits of some decimal number. For example, suppose we want to calculate e squared, or the x of 2. So the x has the value 2. We're going to replace this with 2. So what we have to do is we have to calculate this expression for a given value of n equals 1, and then n equals 2, and then n equals 3, and so on, and keep going, and hopefully the digits that we get will stabilize and give us ultimately a decimal expression. So what happens in this case? Well, in the case n equals 1, we have 1 plus 2 over 1 to the 1. That's equal to 3. When n is 2, we get 1 plus 2 over 2 squared, which is 4. When n is 3, 1 plus 2 over 3 cubed, which is this, 4.629 repeated. N equals 4, 5.0625. It's a finite decimal. or a decimal number. 5, we get 5.37824, another decimal number. And here, 1 plus 2 over 6 to the 6th, well, it's some repeating decimal because it's a fraction, but actually the repeating part is too long to easily contain it here. So what's happening to these numbers? Are they progressing towards some goal? Are they stabilizing? Well, in fact, they are not stabilizing very clearly at this level here. And that's because we haven't chosen enough ends. We haven't gone far enough to even start seeing a pattern. It turns out that the limit of these things is this real number, 7.38905698, and so on. And to get the first 3 digits here, the 7.38, so in order to get 7.38 consistently, you need to go to n being around 1600. You need to go a long ways in this series before you even start getting the first few terms. All right, well, this can happen. There's no indication about how long we have to go before we get to what we want. But nevertheless, this thing does converge. And as we go further and further, increasing values of n, then we're ending up generating more and more and more of these digits. And this is e squared, which is exactly the square of that number e that we had on our previous slide. So, this approach to real numbers as algorithms allows us to define many important functions of modern analysis. So it's a very key application of the idea. A fourth major advantage in this algorithmic approach is that it allows us to define and evaluate integrals. Integrals are a key tool for modern analysis and modern mathematics more generally. So for example, and I'm just giving an overview here. This is not a careful exposition of either integrals or analytic functions or infinite series. So I'm just giving you a taste of some of these ideas. So here's the function f of x equals e to the minus x squared. So it's that exponential function we were considering before with now a minus x squared input into it. If we graph it, we get something that looks like this. It's a famous bell curve shape. And let's say that we're interested in the integral from 0 to 1 of this function. And that means we're trying to estimate or find the area under this graph from 0 to 1. Okay, so there's various ways of trying to define what this integral is. And one way, which was introduced by famous German mathematician Riemann in the middle of the 19th century, is in terms of a limit of approximating sums of rectangles. So what we can think of here is, say, we can divide the interval from 0 to 1 into n equal little pieces. And for each one of these little pieces, we're going to build a rectangle whose height is the function's value at, say, the rightmost endpoint of the interval. So in this case, we get all these little rectangles which are just lying underneath the curve, and we can calculate the sum of all these little areas, and that's what this is. So here is the common width of the rectangle, and here are the various heights of the rectangles summed from 1 to n. The values of the functions, these are the values at these various points of this particular function. All right, this kind of expression cannot be calculated within the framework of rational numbers except in an approximate way. But the real numbers ostensibly give us a way to actually complete the calculation, to get something that's not approximate, but actually something that's exactly correct. Okay, so what ends up happening is that we have to calculate this sum for various values of n. So for example, when n is 2, then we have 1/2 of e to the minus 1/4 plus e to the minus 1. That turns out to be this. When n is 5, meaning we have 5 little rectangles sitting under the curve from 0 to 1. Then the sum of the rectangles is 1/5 e to the minus 1 25th plus e to the minus 4 25ths, and so on up to e to the minus 1. These are the various heights of the rectangles. Work that out, we get something like this. N equals 10, 1 over 10, same kind of sum with 10 terms, we get something like this. We need to make some remarks about the calculations here. So the calculation here is involving already these terms here, which themselves are given by algorithms. So we have an algorithm for e to the x, so we have an algorithm for e to the minus 1/4. And that's the kind of thing that we're using. We have two of those. We have to be able to sum them up and divide by 2 to get this term here. Right. So this is not a case of having rational numbers that we're using. We're already using real numbers at each stage here. And then the idea is to look at these numbers, and as n gets big, to see if they start trending towards some values. And it turns out that they do. You want to go further than n equals 10. So as we keep going, we slowly start converging to a decimal that looks like this. Okay, so this is just a very quick introduction to integration, which we haven't talked at all about in this course up till now. We will eventually talk about integrals. But just to give you a sense of the claim that real numbers as algorithms do allow us to calculate integrals under functions. And this is a primary advantage and good reason for having real numbers as algorithms around. So this is something that a mathematician values highly. We like to be able to integrate. We like to be able to get answers to things like this, and real numbers are seemingly providing that framework for doing that. Real numbers ultimately in terms of an algorithm, because contained in the idea of an integral is really the algorithm described by Riemann, but actually going back to Leibniz. So there are quite a few more advantages to real numbers in terms of algorithms. But they sort of follow the same kind of line, and they're often consequences of the ones I've already mentioned. In addition, we have the advantages that I laid out for infinite decimals in terms of infinite choice in my previous video. We have things like the existence of the intermediate value theorem, which is also really an algorithmic procedure. We have the existence of the fundamental theorem of algebra and factorization of polynomials, which is also an algorithmic procedure. So there's a whole host of mathematical theorems which rely on real numbers, properties of real numbers, which are intimately connected with the algorithmic aspect in this direction that we're talking about now. So we have a lot of good reasons for wanting to have real numbers and wanting to have real numbers in terms of algorithms. However, the painful reality is that there are serious problems. So let's have a look at some of the difficulties. The first is that this theory is very, very difficult to set up. So what are some of the difficulties? Well, first of all, we have to decide what exactly is an algorithm. What are we going to be talking about? What is an algorithm? What is a computer program? What is a procedure? What kind of functions are we going to be considering? When we talk about algorithms or computer programs, we're often thinking about having a certain machine. We're working in C++ or in Pascal or in Fortran or in something. So what machine, what language, what formulas are you going to allow? There are some subtle issues, but important issues, about whether you're going to allow bounded or unbounded running times. So if you have an algorithm, say that generates the nth digit of pi, and I'm interested in calculating the billionth digit of pi using your algorithm, a natural question is, how long is this going to take me? Okay, so the issue here is, do I know ahead of time roughly how long this is going to take me to calculate this billionth digit? For example, you might tell me this is going to take me 24 hours, or maybe 24 days, or maybe 24 years. But if it's going to take me 24 centuries, then I want to know that before I start with the algorithm. And if you don't know how long it's going to take, it might be that your algorithm is such that it's unclear how long it's going to take. It might take 24 billion years. Well, then that's a serious obstacle. So the question is, are we going to specify that algorithms are bounded or unbounded in running time? A related issue is, do we require certificates of boundedness? So if you come to me with an algorithm that, and you claim it's a bounded algorithm, I might want to know, well, are you going to give me a proof of that fact? Or am I just going to take your word for it? So is the proof of the boundedness of an algorithm part of the data that we're going to demand from our algorithms? So let's suppose that we've overcome these difficulties. Let's suppose that we've established what framework we're working in. We know exactly what an algorithm is in this context. We've decided what kind of machines we're working on and so on. And we've answered these questions. Then there are these very, very significant challenges that loom ahead. We're going to have to define, of course, the operations of addition and multiplication, and then ultimately of subtraction and division too, but let's focus on these. So if you have one algorithm for a real number, and I have another algorithm for a real number, so algorithm 1 and algorithm 2, how are we going to combine those two algorithms to give a third algorithm for the sum of our numbers? Okay, my algorithm generates a decimal number, yours does too. If we add those decimals, we're going to get another decimal number, and that's going to be also given by an algorithm. The question is, how do you get algorithm 3 from algorithm 1 and algorithm 2? How do you define this operation at the level of algorithms? And you're going to have to worry that this is well defined, because there are lots of real numbers that have a whole bunch of different algorithms that define them. So you're going to have a check to make sure that your definition of addition of algorithms, whatever it may be, is actually well defined. And you're going to, of course, have to do the same thing with multiplication, which is going to be even harder. And then once you've done that, you're going to have to prove that the laws of arithmetic work. You're going to have to prove the distributive law works for your definitions of addition and multiplication of algorithms. Now, let me point out to you a very serious challenge that you're going to have to deal with. So this is the same problem that we saw with the infinite choice approach to infinite decimals. The problem is, what happens when at the decimal digit level you end up with some 9s? So let's say we're adding these two numbers, and here are the actual decimal numbers. We don't know what the algorithms are, just at the decimal number level. So 1, 8, 8, and here is 1 plus 4 is 5, but the next sum is 9. So we have to check what's happening before we can write down a 5, because there might be a 6 here if that 9 spills over and gives us a carry. And here we have 0 plus 9, that's 9, 2 plus 7, another 9, another 9, another 9, another 9, another 9, another 9. So the question is, what is your algorithm going to do at this exact point right here? Your algorithm for adding these decimals has got to come up with that digit. So your algorithm can detect that there's a 9 summed next, and then another 9 appearing, and another 9 here. And if, for example, it can try to check the next 1,000 or million places. And if you don't get some 9s at some point, well, then you're all right. But if you get a total of 9 for the next million places, at some point your algorithm is going to have to say, all right, wait a minute, we're going to have to stop checking and see whether we can otherwise determine what this thing is. So you have a big advantage working with algorithms rather than with infinite choice, because you know what the algorithm is that generates this digit sequence, and you know what algorithm it is that generates this digit sequence. So in principle, it might be possible for you to analyze those algorithms and see whether this pattern of matching up numbers, adding up to 9, continues indefinitely or not. That's the question. Does this sequence of 9s that we're getting continue indefinitely, or does it eventually stop and give us something else? And because you have the algorithms, you are at least theoretically in a position of checking that by analyzing the structure of the algorithms. But that's going to be a horrendously difficult thing to do. Okay? And probably, to be honest, it's probably not even possible, but let's give you the benefit of the doubt. All right? It's going to be very, very horrendously difficult, and you have to be able to deal with this. So you have to build in to your algorithms for addition and multiplication this exact issue here of how to deal with 9s that appear, that seem to go on forever, but you're not sure. All right, in the year 2012, I'm confident in saying that no such theory exists. We're not even close to having a theory of real numbers as infinite decimals generated by algorithms in this fashion. It just does not exist. No one has come up with such a thing. It's just the reality of it. Now, I think this is a great project. It's a great project in the sense that even if we were able to make some small progress, it would be very interesting. So, for example, you might be able to generate a theory like this that works not with general algorithms, but rather algorithms of a rather specialized kind. Something like repeating decimals, but maybe just a little bit more complicated than repeating decimals. Again, I don't know of any theory that goes beyond repeating decimals, except when you're kind of looking at finite field extensions, which you can encode algorithmically if you want to. But something that's sort of significantly beyond finite field extensions, I don't know of such a theory, but it would be very interesting if someone was able to come up with such a thing. So I don't say it's impossible. Maybe some clever people in the future will be able to derive and create such a theory. But currently, we do not have such a thing. So my criticism of this theory is, in some sense, I'm criticizing something which doesn't really exist. This is a dream. It's a dream currently. So even though it would be great to have such a theory, we do not have such a theory. A second key problem is the non-uniqueness of algorithms. The exponential function, for example, that we talked about earlier, I gave you Euler's definition of it. Here is a quite different definition of that exponential function as an infinite series. In fact, you can sort of see when x is equal to 1, we're getting that value for e that we talked about earlier. All right, so you could encode this infinite series in terms of an algorithm. Then we have two different algorithms that look on the face of it very different, which in fact are generating the same function. Unfortunately, there is no computable way of checking if two algorithms generate the same infinite decimal. There's no way of taking two random algorithms and methodically checking some condition to say, aha, these algorithms generate the same infinite decimal. There's no way of doing that. It's a very serious problem. So to give you an illustration of that, here is a specific example that rests on the classical number theoretical problem of whether there are any odd perfect numbers. So a perfect number is a number like 6 whose the sum of its divisors less than itself equals the number itself. So 6 is the sum of its divisors less than it is 1 plus 2 plus 3. Those are the divisors of 6. And they sum up to 6. So 6 is perfect. 28 is also perfect because its divisors are 1, 2, 4, 7, and 14. And they also sum up to 28. The question is, are there any odd perfect numbers? And no one knows the answer to that famous number theoretical problem. So unfortunately, or fortunately, we can build in such a number theoretical conundrum into an algorithm. So here's a little algorithm. To compute the nth digit of this decimal, let's call it x, here's what you do. First of all, you find the nth odd number. Let's call it k. So for example, if n happens to be 8, the 8th odd number was 15. Okay. Next, you calculate the sum s of all the divisors d, which are less than k, of k. So for example, for 15, the divisors are 1, 3, and 5. We calculate the sum, that's 9. Okay, and we're calling that s. Okay, if s equals k, then we set the nth digit to be equal to 1. And if s is not equal to k, then we set the nth digit to be 0. So here, is s equal to k? Is 9 equal to 15? No, it's not, which is telling us that 15 is not an odd perfect number. So the instruction is to set the 8th digit to be equal to 0. All right, so this is a little algorithm which is exactly going to output 0 here unless the nth odd number is perfect, in which case we'll get a 1. So we know that the first billion, trillion numbers, whatever, there are no odd numbers that are perfect in there. So we can be sure that this number that we're generating with this algorithm starts 0.0000000. It goes on with zeros for at least a few billion. But we don't know whether this number is actually 0 or not. It's given by an algorithm. The algorithm is completely precise. We can code our computer, we can churn it out, but we don't know whether that number is 0 or not. It might be that somewhere way down there, trillions and trillions and trillions and trillions further along, a 1 appears. Okay, so we have no way at the level of algorithms to check whether this algorithm is the same as the 0 algorithm that just says print 0 no matter what. So this is a very key problem. That means that you can't have a surefire way of checking whether two algorithms generate the same decimal number. So these next two difficulties are related. The first is that it's difficult to find a canonical algorithm for an infinite decimal. When it comes to rational numbers, like this one, we can reduce the denominator and the numerator by any common factors, so that we get to a situation where the numerator and the denominator do not have any common factors. And if we also agree that the denominator is always positive, then we get a canonical or standard form for a rational number. So that means whenever we have an arithmetical problem involving a rational number, we can ask for the answer in standard form, which makes it very easy to check whether it's the right answer or not. With real numbers, we have no such situation. There are many different algorithms for a given infinite decimal, and there's no way of saying which one of these algorithms is superior to the other ones. There's no way of singling out a special algorithm that we're going to be using exclusively for that infinite decimal. So it becomes very hard to tell when two infinite decimals are equal. And so when I say very hard, well, it's pretty well impossible. So it's impossible to tell when two infinite decimals are equal. Here's an example. This integral here, or this expression involving 22 over 7 and this integral, that's a real number in the sense of this integral being interpreted in some fashion or another as an algorithm. In fact, there are a whole bunch of algorithms that one can use to sort of unravel what this integral is. But you take one of those and you generate a real number. Here's another algorithm in terms of an infinite series. The infinite series has some binomial coefficient there, 2n choose n cubed, and then a fraction 42n plus 5 divided by 2 to the 12n plus 4. Very curious expression. Then we take the whole thing and take its inverse. This is a formula of the great Indian mathematician Ramanujan. This is a formula that appeared in the University of Sydney exam in 1960. It turns out that they both evaluate to pi. They are both expressions for pi. They're amongst hundreds of expressions that are known. But let's say you were just given these two algorithms and asked, well, are the decimals the same? It would be very, very hard to check that. Some very deep mathematical knowledge is necessary to recognize that both of these happen to be expressions for pi. So one of the consequences of this is that arithmetic with real numbers becomes vague and often almost tautological. Students don't practice doing arithmetic with real numbers because it's almost a non-existent subject, except to the extent that it contains rational numbers inside it. But for example, I've given you this problem in an earlier video to calculate root 2 plus pi plus e in the real number framework. So the modern mathematician really has no answer to that other than to say, well, the answer is root 2 plus pi plus e. That's the simplest expression that we have for this sum. Similarly, suppose you just sort of write down a random infinite series. Summation n equals 0 to infinity, e to the minus n plus 5 times n cubed over n squared plus 1, n factorial. Now it might be that this thing evaluates to some rational number like 3/4. Highly unlikely, but it's possible. But in the absence of knowing some particular special fact like that, we don't know how to sum such series in general. And if a mathematician was asked to evaluate that, about the only thing they could write down is this. I'm going to solve this problem for you. Here's how you do it. Okay, there, I've just evaluated that summation for you. By the way, if anybody knows a better answer, please let me know. Now I'm going to evaluate this function. So here's an arithmetical expression. I'm going to evaluate that here, and this is the best I can do. Again, if you can do better than that, please let us know. And now I'm going to evaluate this. This is an integral. All right. How do we evaluate that? Of course, I could write down a infinite decimal approximation. Okay, but that's only a rational approximation. I can't actually write down that infinite decimal. If I want to say exactly what this is, really the only thing I can do is I can repeat the question back to you as an answer. And finally, in the real number framework, let's solve this problem. 1/2 plus 1/3 plus 1/5. All right, if you're working in the rational numbers, well, then there's only one possible answer. But if you're working in the real numbers, algorithms are fluid, and there's no special choice of algorithms. So in keeping with the things above here, I think a student is justified in writing, well, there it is, there's the answer. Happy students doing arithmetic with real numbers. So I'm being a bit facetious here, but this is an issue. The issue is that we can't actually effectively do arithmetic with real numbers at all. And that's why first-year calculus books, after they introduce real numbers, they rarely ever have a section on, now let's practice a little bit of real number arithmetic to get you used to it, to get you understanding how it works. There's never a section like that because the arithmetic is vacuous in some sense. Okay, it's a necessary consequence of this imprecision that we get when we look at things with an algorithmic point of view. Now, there are many other difficulties that arise in mathematics as a consequence of this point of view towards real numbers. But I'm going to stop here. These are sort of elementary considerations that are right close to the core of the definition. So I think the overall argument that I'm making here is that trying to define real numbers in terms of algorithms doesn't work. It has not been done. There are too many technical obstacles, and people just are playing some fantasy game when they talk about this theory as if the theory is already there. The theory is not there. Even though we would very much like it to be there, because that's what we use to do our infinite series, to do our function evaluations, to do our integrals, and to do many other things. So we see a serious disconnect in modern mathematics between rigorous thinking and the practical application of what we're doing. Now, most pure mathematicians are going to be reluctant to face the music here. The idea is to avoid thinking about this problem because most mathematicians are aware at some level that it's there. The agreement has been to let's not think about it too much. Let's call all such discussion, oh, that's philosophy, or that has to do with foundations of mathematics, which doesn't need to concern us. But it ought to concern us very much because it has very serious consequences for mathematics. And once you're going to start adopting a lazy attitude towards rigor at this level, it starts infiltrating in other areas in mathematics. Students learn that there are certain places where it's allowed to be waffly, where it's allowed to be sort of hand-waving. It's not an ideal situation. I think next time what we're going to do is we're going to look at a very important object historically, and one that many of you will probably like very much, this magical object called pi. Is it really a number? That is not so clear. I'm going to introduce the idea that maybe pi is something slightly different from a number in the usual sense. So we're going to have a historical look at formulas for pi. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.